Hey guys, welcome back to another episode of Simulaos. I'm gonna be totally completely honest, my voice is killing me today. So if I sound a little bit weird or if I'm not able to complete a couple sentences, I don't know. My voice is just gone today. It's okay, I'm sure it'll be back eventually, but yeah, that's kind of an issue. Anyway, what are we going to do today? Well, we're going to talk again a little bit more about dynamic Huffman encoding. Oh, sorry, what am I doing here? So let's go ahead and open up Zernal a little bit, and let's talk about it. Not as much as we did yesterday, but we should still talk about it. And of course, if you guys have any questions, let me know as we're going through, because I'm going to go through the basic premise, what it is we want to do with this algorithm, and how we intend to do it. So, 1 second, let me get a sip of water, and let's go ahead and get started. Alright. Good. Okay, so let's go ahead and start by talking about the regular old Huffman algorithm. So the regular old Huffman algorithm is, well, in a sense, pretty simple. My idea, or rather, what I think, is that most people have been taught the Huffman algorithm at some point in college, right? So let's talk about it. Huffman algorithm. The idea is simple. We have a string of letters, A, B, C, D. Let me check my stream real quick, just to make sure everything's good. Okay, we have a string of letters, A, B, C, D. And we want to convert these letters into a string of bits. Let's say, I don't know, 1, 1, 0, 1, 0, 1, 0, 1, 0, 0, or something. I don't know. Just made up random bits. This is fine. This is one way to do it. Just by kind of creating some sort of random library or something like that, random list of code words. Hey, I love Twitch, what's up? So, we could just imagine a kind of cipher here. So A, B, C, D, where we say A is going to be 1, 1, B is going to be 0, 1, C is going to be 1, 0, and D is going to be 0, 0, right? But this isn't the most efficient way to do it, because in essence, there are an infinite number of different code words that we could choose, and none of them really work out the way that we want them to work out. Rather, how do I put this? There is an optimal way to do this. Now, Huffman encoding will not give us necessarily the optimal way, but it will give us something that's pretty close for large alphabet sizes. So, how is it done? Well, in this particular string, we go through... Sorry about all the coughs, guys. We go through... and we kind of first check the entire string. And we say, well, A, getting into statistics and Bayes theorems, and then getting into machine learning. Oh, cool. Yeah, machine learning is awesome. I know a little bit about Bayes theorem and stuff like that. I took a adaptive systems course in university. It's really cool. I wish I knew more about machine learning. In fact, it might be something we do on this channel a little bit further down, because I don't know, I just find it really interesting. It's one of those things, there are a few algorithms out there that just seem like black magic to me. Like, I don't know how they work, but they produce fantastically beautiful results. And there's just a few things. Like, for example, DMRG is one of those algorithms that we did a few days ago, or a few weeks ago. Black magic to me. I still don't know how it works, even though we implemented it on stream. So I have another paper out that I'm reading right now from Matrix Product States, which will hopefully help me understand that. A while ago, Quantum Monte Carlo was just completely black magic. Lots of things. Imaginary time. Let me see. Imaginary time. What's it called? Evolution. Another thing. So, I don't know. I just find a lot of weird algorithms like that. Of course, because I'm a quantum physicist, that's the kind of stuff that interests me, quantum physics, but other things interest other people. Anyway, back to Huffman encoding. We go through the string once. We count the total number of strings and the total number of A, B, C's, and D's. A appears 1 out of 4 times, so it has a frequency of 25%. 1 second. B appears once, so it has a frequency of 0.25%. C appears once, so it has a frequency of 0.25%. And D appears 1 time, so it's a frequency of 0.25%. Now what we do is we go up and we add up all of the lowest valued leaves here. So here we have 0.5. Now the two lowest valued are these two, 0.5, and then these two right here as 1.0. We go back through the tree. labeling them as 1 0, 1 0, 1 0. And then we create our cipher here, which is A as 1 1, B as 1 0, C as 0 1, and D as 0 0. And that is our code for this particular system. Now, there's a couple problems with Huffman encoding. Huffman encoding is great. It works very well if we have the entire string beforehand that we are reading in. In that case, it's fine. We just go through the string once, and we do what's called two-pass Huffman encoding. We pass through the string once, we find the frequencies of each of the individual letters, and we use that to construct our Huffman tree. However, let's say we have a huge string of letters coming in. We don't know how long the string is, let alone what the frequency of each individual character is within the string. In this particular case, we need to use something that is a little bit different. We need to do something that is dynamic, something that doesn't need two passes but only needs one. And this is where dynamic Huffman encoding comes in. 1 second, Huffman encoding. So here's the thing about dynamic Huffman encoding. There are ways to do it. There's one called the FGK algorithm, which works decently well. The one that most people use, though, is called the Witter algorithm. Witter algorithm. Now, we went through this in good detail yesterday, so I'm going to kind of, I'm going to kind of briefly go through it today, hopefully helping you guys understand little bits and pieces that you may have missed yesterday. So, every time we build a tree, we will do a couple of different things. One, we will implicitly number the tree. How about implicit numbering? And this is because basically, with any given tree, we can go through and give these guys a set of numbers. So I'm going to put this up over here. And the idea is this. So here's the tree we had before. 1, 2, 3, 4. Okay. What we'll do is we'll go through and say 0, 1, 2, 3, 4, 5, 6. That's all we need to do. So going from this way to this way, we increase in number, and going from here to there, we increase in number. So the increase in number is from left to right and down to up, so that the root node always has the highest weight. And this helps us define what are known as blocks. Blocks are basically any element within, any set of elements within our tree that share the same number and also the same identity. So, for example, if we have a whole bunch of ones down here, let's say 1, 1, 1, 1, all of these guys would be in the same block. However, if let's say this was a 0, and we had a 1 up here, this guy would not be in the same block as these guys, because this guy is inside of the tree while these guys are leaves. So we make a clear distinction here between leaves and internal nodes. I might call them external nodes for leaves. It doesn't matter. We have external as leaves and internal as, well, internal nodes. And the blocks are defined based on that. Now, the next thing we have, obviously, leaders of the block, which I'm going to put over here. And finally, we have different methods that we have to take into account to work with this. That's slide and increment and a few other things. I'm going to very quickly show you how the algorithm works, and then we're going to go ahead and get started. So here's the idea. Let's start with a simple phrase, HELLO. This is dynamic Huffman encoding, so we don't know the frequencies of any of the letters at this point. All we know is that we don't have any letters, so we have a 0 node. Okay? So what we do is we create an H node, which has weight 0 inside of it, and an additional 0 node over here. Now, what happens? Well, we move this block here, or this internal node, to the front of the next block of external nodes. So, in front of all of the leaves of weight 1, there are no leaves of weight 1, so all we do is increase its value by 1 and this value by 1. Okay, next, what we do is we add in the E. Very similar to what we did before. We put a 0 here, we add another 0 here, an E0 here, and we have our H1 here. Okay, so now we move this node in front of all leaves of weight 1 because it is of weight 0, which means our new tree is going to be 2, H1, 1, 0, E1. Alright, sounds good to me. Next tree, it's going to be, we add in a 0 and an L here, L of 0. Now, this one's a little bit complicated. We need to move this 0 node in front of all the leaves of weight 1. So we have to move it in front of this guy here, which means this guy has to move somewhere. It's going to move to this guy here. And this guy then needs to move somewhere, so it's going to move over here. This is the first example of what's known as the slide in increment, where we slide everything and increment our value by 1. So, the new tree is going to look like this. 3, 1, L, 1, sorry about that, 0, 1, E1, and of course, H1. Oh shoot, I did this backwards. H1 and E1. Okay, so that's our new tree. Now we have an L. And you might think, oh, it's an L, this will be easy. No, actually the L is a little bit difficult. So when we get a leaf node that we already have in the tree, here's what we need to do. The first thing we need to do is switch the leaf node with the leader of its block, which in this case is just H1. After doing that, L1, H1, we then need to switch it with, 1 second, this is actually a 2, my bad. Okay, we then need to switch it with the leader of the next block of 1s, which will be this guy right here, which means this guy then moves over here, giving us a new tree of this, 4, L of 2, because it took over the previous spot. I can draw that box a little bit better. L of 2. Now we have 2 in here. It's going to be, let me see here. E1 over here. Then it's going to be 1, 0, and of course, H1 over here. Okay, so now we have one last thing to do, which is add in the O at the end, and then after that, we'll have sufficiently encoded the phrase hello one more time, just to kind of relate it back to yesterday. Hey Gustor, and thanks for coming in. Okay, so let's go ahead and add in the O. We're gonna have an O0 down here. Forgive me that it's at the bottom of the screen, and a 0 node here. Okay, so now this guy needs to move up here, to the start of all of the leaf nodes of weight 1. And yeah, so now we have up here, I'm just going to write it here, 5 of L2. Yep, L2. 3. Then what is it? It's going to be 1, 1, 0, 1 second. Then it should be 1 second. This one's gonna go here, right? So then this guy has to flip over there. Okay, good. So it should be E1. Oh, wait a minute. 1 second. Oh, sorry. 2, E1, H1. Where we did the same thing we did before. This guy moved over here, and this guy flipped over there. Good. Hey, Mathnex. And there we have it. A somewhat simple adaptive Huffman algorithm to use. It's actually not that simple. It's quite complicated. So I'm going to pause for a minute to see if you guys have any questions before we get into the coding. Again, guys, my voice is shot today. I have to apologize for that. I don't know what's up. Yesterday I had a bit of a problem with my throat. I'm not sure exactly what was going on. If it gets too bad, I might have to close the stream a little bit early, but I don't think that's going to happen. It seems fine enough. It's just, I don't know, it's kind of bugging me. Okay, again, I'm going to get a quick sip of water, open up the blinds, and then we'll be good to go. Good. Okay, so let's go ahead and pop this over to this desktop, pop that over to that desktop, and let's just talk about things really quickly. So I'm going to cd into projects, Simuleos, and of course the Huffman directory. We're going to cd into projects, Simuleos, and of course Huffman. Good. Now we're in the appropriate directory. Oh, what was that? 1 second. There we go. Now we're in the appropriate directory. Let me go ahead and open up a couple of files here. So let's go into the Huffman.cpp file because that's the one that we stopped working on yesterday. And just to be clear, in case you're not sure as to what it is that's going on in the animation to my, what is it going to be, right? It's left for me, but I think it's right for you guys. Let's go ahead and open up that image. So if we do Mirage, frames, animation.gif, this is a very simple animation of standard Huffman encoding where we draw all of the wait 1 second, where we draw all of the external nodes, then we draw the internal nodes that connect them all to the root of the tree, and then we go from there. Let's see, what is this? Kyowa Supaidoman. Oh, I see. Okay, and this is the animation that you see to my right. Okay, so I don't know, why does everyone think I sound like, or I look like Spider-Man? I don't actually know what Spider-Man looks like, so I'm not sure what that means. I don't know if it's a compliment or an insult. I have no idea. I know Peter Parker is like super smart, so that's good. But I think he's actually the second smartest. Oh, is it Konnichiwa? It might be. I'm sorry, guys. I'm bad at Japanese. I need to learn more. I've got my manga set over there. I've got my let me see. What is it? I've got my books that I need to learn things with. It's all there, but I just don't see Japanese enough to actually know it. Even though I'm in Japan, you know, you'd think I know more. It kind of depends on what I want to do here. Actually seems like something Peter Parker would do in his free time. Maybe, I'm not sure. This actually seems like something that, I don't know, Peter Parker would probably be like building things. He's not really, is he much of a programmer? I didn't think he was much of a programmer. I thought he was more of a, like an engineer type of character. Anyway, so what are we going to do here? Let's go and open up Huffman.cpp. And let's talk about what we were doing before. So before, we have basically two codes here that we're working with, Huffman.cpp and Vidder.cpp. We also have Huffman Visualization.cpp, but the Huffman Visualization is, as you might expect, specifically for the visualization. It's after the Huffman tree has been built. So what we need to do is go through and figure out what we want to do with, let me think here. How we want to test. Man, I'm super yawny today. How we want to test the Vidder algorithm. So, what we need to do that to start is to create a Huffman tree with a vector of internal and external nodes. And that's kind of what we're working on right now. So let me see. I have a note up here on Huffman.cpp that says binary tree not implemented yet, but it is implemented. So I'm going to remove that note. I don't know why it's there. Huh. Create a simple Huffman tree given a likelihood of receiving certain characters. Yes. How deep are you allowing the tree to become? Is it static or dynamic? Well, maybe I'm misinterpreting the question, but at this point in time, the first Huffman tree that we're creating, just to do a couple quick tests on some of our early Vidder algorithm stuff, is going to be a static Huffman tree. However, from there, it's going to be dynamic. There is no limitation on how large the tree can become. The tree can be as large as it needs to be. But it will be a dynamic Huffman tree in the near future. I'm not going to say necessarily today, but maybe by the end of this week or next week we'll get it sorted. There's a couple of different issues that I know we're going to run into that I'm probably going to need some people's help on, but that's okay. As we get to them, we'll get to them. Alright, so yesterday we did a good bit of code cleanup. Now we have a whole bunch of other stuff we need to work on. The height of the Huffman tree is inherently limited by the alphabet used. Yep. Okay, so what are we going to do here? Huffman, there we are, Huffman. Okay, so you'll see here that yesterday we read in the two different vectors, internal and external. And of course, when we call Huffman, let me go down to Huffman here, 1 second. Huffman there. Let's see, what am I looking for? I'm looking for one particular call of Huffman. Initial nodes, internal, external. Yeah, so this call of Huffman, we have to go ahead and initialize our internal and external nodes. And this is what we did just right here. So we have our internal node, we did reserve, everything else from there. But at some point the tree could get too deep where it becomes overhead, more overhead possibly. I guess so, yeah. But let me see. Even with Japanese and Chinese, the tree wouldn't get that deep. That can be inferred from the fact that a binary tree is used. Yeah. Let me think. So, I mean, it depends on how often the characters are used. If you've got like 100 characters and one character is like never used, and you can somehow, yeah, I think Gustron's gonna be right, but we'll see. We'll see in a bit. We can add in a super large dictionary, and we'll see what happens there. Anyway, guys, so we went through and we reserved the space for our internal and external nodes. Now let's go through and work on the Huffman algorithm itself, or the Huffman function itself, so that we actually manipulate the internal and external. So let's do Huffman. 1 second. Huffman x whatever. Oops, my bad. Huffman. 1 second. Wait, what? 1 second. Let me just go up and find Huffman. I don't know why I'm not to leave parentheses here. It's kind of weird. Anyway, so Huffman. There we are. Death first search. Huffman, here it is. Okay, so what are we going to do? Well, at this point, we already have a node queue of all the initial nodes. By initial nodes, we mean, what do we mean? We mean all of the external nodes. So that's kind of what we're working with here. So we have all the external nodes, and what we're doing is we're going through and we're popping them, right? Now we already have space for all of the internal and external nodes, and we have a big while loop going through everything here. So let me go through here and let me create 2 different counts. So counts for the internal and external, what do I want here? Internal and external vectors. Okay, so now we're going to go through, and every time we check the top node, top 2 nodes, I suppose, we're going to go through and we're going to check to see if they're internal or external nodes. And then what we're going to do is, after checking to see if they're internal or external nodes, we're going to set the value of one of our internal or external vectors to be that character. Now, this should, let me think, this should go through and give us a vector that is automatically of the appropriate, because the node queue is already aligned appropriately. I think all we need to do is put these into the appropriate vectors, and we'll already have a vector that is appropriately weighted. Yeah, Vitter does, definitely. The FGK does not. So the Vitter algorithm does a pretty good job of doing what it can to optimize the code itself. Let me think. Yeah, as an example, let me see if I can find the Vitter paper for you guys. So let's go over here. Let's open up a new tab, and let's go down to this one right here. Here is the Vitter algorithm, the one that I'm getting a lot of information from. And let's see. Let's go to one of the FGK. Let me see. Huffman tree for algorithm FGK. Here. So this guy right here, figure 5. This is one of the Huffman trees. Let me go ahead and zoom in a little bit. For the FGK algorithm, which was the first dynamic Huffman algorithm. Now if we go through, let me see if I can find it. Should be down here. Here. Okay, and this is it for the same set of characters. So you'll see that this one is split into 2 branches and is much shorter than what we had before, which was up, 1 second, up here. So that's the idea. Realize a potentially more efficient way of generating the Huffman tree. If you found a potentially more efficient way of generating a Huffman tree that beats the Vitter algorithm, I'm pretty sure that's a pretty high impact paper right there. So let me know if you did. Okay, so let's go over here. And again, guys, I apologize if I sound really out of it or off, because my voice is my throat is just killing me right now. Okay, so node 1, we have node.top. Oh, okay. So what do we want to do? Initial nodes.pop. Here, when we define the node.top, we're going to check to see if node is an internal or external node. Okay, so what we're going to say Let me see. The external nodes are the only ones with characters. So let's go into vi Huffman.h and let's see what we got. We have key. So we'll say, if you're inserting nodes after sorting it, couldn't you just use a flat array for the binary tree and sort that? Let me see. If you're using, if you're inserting nodes after sorting it, couldn't you just use a flat array for the binary tree and sort that? Let me think. I'm not sure. Let me see. Oh, in the static Huffman one, we're never inserting the nodes. That's not what we're doing. This is actually a special case that we're adding in, so we can later test the Vitter algorithm. At this point in time, we never actually add the nodes to an additional vector. So all the stuff that we've done so far with the Huffman algorithm is totally correct with the Huffman algorithm, but it does not involve at all inserting the nodes after sorting it. This is something that I'm doing specifically so that we can test particular functions of the Vitter algorithm as we go through. Just pointing that out. Okay, so check the internal, check to see if the node is internal or external. Okay, so what are we going to do? Basically what we're going to say is if, what do we want here? Initial nodes dot top is, let's see, dot top. Let me see, dot key here. So this means there is a key. And let's go down here. There. Okay. So now we're going to say if there is a key, then we are an external node. And we'll just kind of comment this in. External node. And then let's go here and let me see. We have in our external node. What do I need to do? I just need to set the first value of, let me see. Where are we? Counts for internal external node. We're using one array? One second, let me think. I didn't know we were using an array. Okay, so let's go down here. Let's add in the count. So let's do in count. One second. Int count internal and count external. And we're going to set both of them equal to 0. Equals 0. Okay, so now let's go down here, internal node, or external node. So what we're going to say is external, one second, external of the value that we want to read in. So we're going to say count external. But you can figure out the nodes by index arithmetic. This tree isn't complete. Wait, what do you mean by this tree isn't complete? I apologize, I'm not fully following the conversation. It's possible to store an n-depth binary tree, an array of size 2n minus 1. Yeah, that's fair enough. Okay, so let me see. I'm not exactly what you need to raise priority queues to generate a static tree. Okay, so let's see what we got here. Count external. This is going to be equal to, what do we want here? Initial nodes dot top. And then we're going to say count external plus plus. External plus plus. Okay, let's go down here and let's add an else statement. This would be an internal node. Go down here. We're going to say internal node over here, and we're going to say internal of count in. One second. Count is, yep, that's exactly what I said. It's going to be equal to initial nodes dot top. And then we're going to say count in plus plus. Good. After this, we pop it. A complete binary tree will have the maximum number of nodes at each level, except for the leaves. Let me think. Wait, we don't have a maximum number of nodes at each level? Oh, I see what you're saying. Yeah, you're totally right. Yeah, you're totally right. Gotcha. Okay, so let's go here. And let's add this in one more time. Right there. Good. So this should give us our internal and external nodes. So what we want to do is go up to, let's go ahead and write this. Let me go ahead and make this just to make sure the code makes. Okay, so obviously I screwed something up here. If initial nodes dot key, let's go to, I need a point, obviously. Go to 93. Because I forget about things. So let's go here, add a pointer. Make it again. Let's see. So expected semicolon at 102. Yep. I would too if I were you. And then we go here. Let's go ahead and write that. Let's make it. And this one I think should make. Good. Okay. Jack and Jill went up the hill to fetch a pail of water. Jack fell down and broke his crown. Jill came tumbling after. That's incorrect. That encoding phrase is definitely wrong. Also, you want to sort nodes by weight. It might be easier just to store them in a map with keys as the weight. We do have that, actually. But I think it's the other way around. I think it's the characters of the weight. One second, let me go through here and let me check something. Let me comment this guy back out. And let me comment this out. Oh, wrong way. Let's do the same thing down here. One second. Let's make it one more time. What should I do? Let me see. Opening that one, closing that one. And let's make it. Okay, a couple things that are warning. Okay, so for some reason this one makes, but the other one does not. Not sure exactly what we're doing here that's different. So we're saying if internal nodes.top, if there is a key, we are going to be an external node. Weights don't have to be unique. Oh, yeah. Okay. So, let me see. Jack and Jill went up the hill to fetch a pail of water. Jack fell down, broke his crown, and Jill came tumbling after. And that is our encoded phrase. Now, here's the thing. If we... I don't understand why, but if we go through and we set these guys up, so if we start doing this, and this is completely bizarre to me, so there's something here that I'm just not fully understanding. If we now do this, which all I'm doing, guys, is I'm going through and I'm saying if there is a key in the internal node, you can throw a map to an array of nodes, which might not be a bad idea. Let me think. So let me write this. This is completely weird, guys. An internal nodes.top key. So we're asking, does the internal node have a key? Then we know we'll be in the external nodes, and we put that into, hey Woody Bents, we put that into an array for the external nodes, or a vector of the external nodes. Then we do the same with the internal nodes. So we say, okay, well if there is no key, then we must be in the internal nodes, and we put that node into the internal nodes. Now here's the thing, for some reason when I run this, let's go over here to make, everything's broken and I'm not sure why. So you'll see here that the encoding phrase is clearly not what it's supposed to be. It's a whole bunch of ones and it doesn't know how to decode it at all. This is bizarre. I have no idea what the issue is. I think you'll end up doing much less work with a flat array. Multi-map? I don't actually know. Let's see what the multi-map is useful for. Hey Gusman, why do you hate working with an unordered map? I use an unordered map every once in a while for work. I'm a little bit confused, or I wonder what the reason is there. Hey Novelus, and Witty Bents, I don't remember if I said hey to you. Hey, thanks for coming in. Alright. Good. Again, guys, I apologize for being rude and every once in a while just pulling out my water and drinking it. My throat is killing me. I don't know how far I'm going to be able to go with today's stream. Hopefully we can finish it up, but we'll see what we need to do. Okay, so first mystery of the day. Internal nodes.top. Every time we do this section of the code right here, before popping the internal nodes, initial nodes, we have a problem. Have you heard about the 60 Symbols Fellowship? I directly had to think of you. Actually, I did think of the 60 Symbols Fellowship. The problem is that I'm a PhD student right now, And I still have a few years before I finish up my PhD. So the Ogden Fellowship is for those who have already done one postdoc or are just finishing up their PhD right now. Because I still have a few years, I can actually wait until the first fellowship is over with, see how that goes, and then apply for the second one because they say that it's a 2-year long fellowship. And I think if I continue doing streaming and I continue doing the YouTube channel and stuff like that, I think I'll be in a pretty good position at that point to apply for that. However, I also don't know what the UK will be like in 2 years, so I kind of feel like I'd like to wait that out too. You know, see how the academic environment is there and stuff like that. On the one hand, if Donald Trump is elected president, I certainly don't want to go back to the US. On the other hand, if the place I want to go to is the UK, I have no idea. So we've got time. But yeah, it's definitely something I have on my radar as something to look into. Okay. So, internal and external nodes. I have no idea what's happening here. So again, guys, let me see. Because the unknown map API is terrible, operator automatically creates an element for you, checking a key exists is ugly, and it exposes the underlying implementation for no good reason. Okay. Okay. So internal nodes.top key. Not sure what's going on here, so this is what I'm going to do. Let me go through into external count external. Let me go down here and let's std cout. Cout. And I want to output external of count external. And then I want to point this to, let's do wait. Good. And then let's end line. And let me do the same with the internal nodes down here. So we're going to do std cout internal of count internal. Then we're going to say pointing to wait. And then we're going to end line. Go down here, add them down here, and then we're going to see if we can figure this guy out. So copy this, put it down there. This one case, we're using pushback might be easier. I'm not sure. Why would pushback be easier in this case? If there is a legitimate reason why, that's fine. But we already have. Okay, so let's go ahead and make this. Give it a second to run. Segmentation fault. Okay. Well, that's interesting. So we say external node of count external. Let's go through and just output count external and count internal then. Let's not worry about anything else. So you count external and count internal. You don't have to worry. But keeping count of the track is, I don't know, it's not particularly difficult, I don't think. So we'll do count external is, one second, count external. Down here we'll say count internal is, and we'll see what's up. So we're going to say count internal, yeah, let's just do it this way. One second, count internal is, one second, count internal. It's kind of weird. Like every time I think we're going to get somewhere with this code, I always break something, and now I don't know what's happening. So let me go here, and let's see. So we know what count oopsie, that was not what I meant to put down. We know that count internal and count external will be, oops. Count internal and count external will be, we know what they're supposed to be at the end. So we can very easily check to see if this is correct just by checking that. So it's right here, let's make it. Okay. So let's see, count internal is 22. Count external, whereas last count external is 24. So we're actually off by one. I'm not really sure what you want to do. You're overriding internal nodes with external nodes and vice versa. No, I'm not. One second. I'm not sure what you want to do. What I want to do is put all the nodes into an array. That's all I want to do. You're overriding internal nodes with external ones and vice versa. I just wanted to put all the nodes into an internal external node vector so we could more easily parse through it later. Again, this is just a test for the Vitter algorithm because we already have things that find like block leaders and things like that, and we're going to have to very easily figure out what is in each block. So, again, all I'm trying to do here is put them into vectors. which I thought was exactly what I was doing. So let me see. So the first thing we do is we check to see if it's an internal node or external node. I mean, you're fine. I thought I was doing things wrong, which I'm clearly doing something wrong here. Okay, so we have internal node count as 22. I guess that might be fine. The external node count is 24. It should be 23 for the internal nodes, but that's fine. We're off by 1. That's not a huge deal. Okay. So initial nodes.top key. This means we should be an external node, but for some reason, let's go through and let me check something. Instead of outputting, yes, did I link it before? No, I did not. My apologies. So let's go here, post it here, and let's go from there. Again, what we're trying to do right now, in fact, there's another paper out there that I should probably get to. Let me see. I have it over here. Let me get it. I'm actually really looking forward to the next algorithm when we start getting back into physics and stuff. Not that computer science isn't interesting, it's just it's really hard for me to follow. So at least with physics algorithms, I know what I'm getting into, you know? Alright, good, found the paper. So it is, let me look it up one more time. Algorithm 673. Algorithm 673, dynamic Huffman encoding. Should be this one right here. And here's a Pascal code implementation of the Vitter algorithm. So hopefully that will help out. Okay, so now the mystery, the thing that I can't figure out. Let's go through and let's work on this. So first what I want to do is before ever doing this, in fact, let's just comment this out. Let's go here. Okay, that was not at all what I anticipated. Thought I pressed in capital I. Hey, Love Feelings, what's up? Let's go here. Let's do that. Nope, this is for some reason not doing what I want it to do. There we go. Dot. Okay, good. Let's go here, there, there, and there. Okay, now let me just output something real quick just to see if this screws anything up. So I'm going to say initial nodes. 1 second. Nodes dot top. Pointing to key. No, let's do weight because everything has a weight. End line. And you'll see what I'm doing in just a second. I apologize. STD cout initial nodes top weight. Okay, let's go down here. Do the same thing. In fact, we can copy the same line and let's put it here. Now we're going to go down here, do the same thing again. I just want to output all the different weights and see if we are actually outputting what we anticipate. So right here, let's go to make and let's see what happens. Okay, so we are outputting 96 as the final weight. Now, this is the thing I just don't understand. What is happening here? Why is it that anytime I look at the initial nodes, dot top, why does it overwrite? What is happening to the initial node top after doing this? I have no idea. I'm not very good with queues and such. So let's go and let's just comment this out entirely, and let's see what happens there. 1 second. I need to put a period there, and period there. Okay, so now all I'm doing is I'm checking to see if the top node has a key in it, and then we're going from there. So let's go to make one more time. Okay, so this is kind of what I suspected, but I'm really not sure what's going on here. So instead of using initial nodes.top, let me just use node 1, because this should probably solve our problems. So node 1, and let's go down here to node 2. 1 second. Node 2. 1 second. Wait a minute. Node 2 is initial nodes.top. Node 1 is initial nodes.top. Oh. Let's write this, go over here, make. node dot top. Oh, of course not. Node 2 not dot top. And again, guys, if I'm doing something that's super confusing, let me know. I'll do my best to explain it in chat. Unfortunately, you guys have come in the middle of... Yeah, so I think I figured out what I did. I think I was redefining... No, I'm not sure. I have no idea. But since we defined node 1 as initial nodes.top, we should be okay just to use node 1. It's not a horribly big deal. So let's go through and let's work on it from there. So we are not going to worry about outputting the weight. Let's just go ahead and do external is count external initial nodes.top. But nope, this is going to be node 1. Node 1. And then we're going to see out that particular node's weight. So let's do external of count external, and then what do we want? Count external, and we want to point to its weight. Same thing down here. Delete this line, go down here. Count internal is, no, we can go ahead and get rid of that line. Count internal is going to be equal to node 1. 1 second. 1, and then we're going to output some stuff. So we're going to do std cout internal of count in pointing to weight, and then new line. Let's go down here and let's do the same thing. So we're going to delete these 2 lines, remove these, go here, and let's output its weight and see what's happening there. Output this guy's weight, go down here, remove a few characters. 1 second, where are we? We're up here. There. So let's go ahead and write that. And let's go over here to make. Let's see what happens. Okay, this one seems to make just fine. Now let me see. What is the... oh, wait a minute. Why are we not outputting... 1 second. Are we outputting the weights? That's the question. And I guess maybe we are. Let's go up here. Yeah, so that has to be the weight then. 71 has to be the final weight. Let me see. Q will always return the same element for top. Yeah. So I don't know what the problem was there, but I do feel like whatever it's doing, whatever we did, it's now kind of sort of fixed. So I'm okay with that. Okay, so what are we going to do next? Well, let's go through and make sure all these weights are correct. So 71 is here. Let's go through and at the end of Huffman, where are we? Initial nodes.top. You know you're destroying initial nodes in the process? Yeah, see, that's the thing. I didn't know that. So apparently every time I call top weight or something like that, I'm destroying that value. I'm not sure how that works. I thought we could just peek. Wait 1 second. You might, but I want to make sure. 1 second. You might, but I want to make sure. Yeah, so in this case, because we're doing Huffman, the Huffman algorithm, we are supposed to be destroying initial nodes. In fact, this is one of the few cases where I did not want to use an ampersand sign for the initial nodes because we would be destroying those nodes afterwards. But it's okay. It doesn't matter. You're not destroying the value. You're removing it from the initial nodes. Might also be true. I'm not sure. What I do know is that every time we called like top weight or something like that, we were not able to use that particular system. Hey, Ginfiro, it's been forever since you've been here. How are you, man? Okay. So let's go through. Actually, guys, give me 2 seconds. I will be right back. Sorry about that. I've got like a really stuffy nose. Give me just a second. Again, 1 minute. Okay, I'm back. Sorry about that. Again, I just feel a little bit sick today, but that's okay. It's not horribly sick. Everything should be fine. Good. So, let's keep going. So we have the Huffman tree here. What I need to do now is print out the total, I suppose, the total weight or the weight of the root node, just to make sure it is 71, because I feel like for some reason 71 isn't right. You could completely rewrite the code in 3 lines. I could, maybe. Let me see what 3 lines you suggest. Okay. So, Good. Okay, so let's go through and let's see. We know that the final weight here that we have down is 51. Auto node, initial node's top. Let me see. Node key, external, internal, pushback node. Wait 1 second. Node key. Oh, is there a node key? External, internal. Then we push back node. Initial nodes pop. Honestly, that's fine. That is definitely a way to do it. I honestly try to avoid using the question mark though. Yeah, you're totally right. I could do that. I don't know. Yeah, that's fine. That's fine. I could totally do that. I just have a lot of trouble reading the question mark. I don't know if maybe it's because I'm just so bad at programming. I always have trouble with it. But anytime I see that question mark, I always have to think a bit, as to what we're actually doing. Okay, so let's see. What do we want to do? What I need to do is go down. Here we see the final tree root weight is 121, which is clearly not the root weight we have here. So something is up. I'm not sure what. If node key, external pushback, else internal node, internal pushback node. Again, why would, in this case, I see no reason why we'd want to be using pushback since we know, the weight here. Let's see. Ternary operator sometimes results in more efficient code, particularly on Intel systems, since it directly translates to a conditional move instruction. Ginfer, what are we using Huffman for? We're actually just learning the dynamic Huffman algorithm right now, the Vitter algorithm, which I have linked previously. If you're interested, it is this one right here. We're just learning the algorithm. Kind of similar to how we normally learn physics algorithms. Here we're just learning a computer science algorithm. Let's see. After that, we're going to go back to some physics. I have some good ideas of what I want to do next. Super excited for that, so we'll see how far we get. Okay, internal node size, greater than 1. Let me see. Let's see. Ternary operator. Ternary operator is what? What is the ternary operator? Sorry, I don't know that. CMOV, 2. What is CMOV? Again, guys, my background's physics, not computer science, so every once in a while, I miss a few words here and there. If else statements to CMOV. Let's see. Computer. Oh, okay. That's the ternary operator. Sure, fair enough. Okay. I should have known that one. I feel like I knew that one. Okay. So, the final weight is not what we want it to be, and that is a little unfortunate. So, let me think here. How do we want to go from here? We have 71 plus 50. That's going to give us a total of 121 if we add them together. So, the only one that we're missing is actually the root node. Is that correct? Let me think. I thought in this case, since we don't have to use pushback, we shouldn't want to use pushback. Wait. It's just as efficient as indexing. You call reserve in advance. Yeah, I guess that's fine. Fine, we can use pushback. It's okay. So let's go here. External count, node 1. Okay, so let's go here, remove the counts. Let's go here, stdc out. Let's see. It's just as efficient as indexing if you call reserve in advance. In this case, it'll result in more concise code, even though using the result as a ternary operator as an L value is a bit of a hack. As an L value, okay, left value, I guess. Okay, so let's go here, external.pushback node 1. Let me go back down to where we were. Where were we? We were right here. Remove the counts. Okay, we have external node 1. What do I want here? Let's remove. What do I want? I want external.pushback node 1. Good. Let's go here. Remove this line. Internal.pushback. 1 second. Pushback. Node 1. DD. I managed to get 20% performance increase in my lock-free hash map implementation. I wouldn't call it, doesn't matter. Let me see, what do we have here? In this case, it also results in more concise code. Okay, fair enough. Okay, so let's do external.pushback node 2. Oh. Oh, well, that was a mistake of mine. Dot pushback node 2. 1 second. And then remove this line here. And we do internal.pushback. 1 second, node 2. Dot pushback node 2. Okay, and let's remove this. Now, one thing I'm thinking about here, guys, we are missing the final node, which is the root node. So let me think, is there a way, is there a way to go ahead and add in the root node here? So I guess what I'll say is while initial node set size is greater than 1, and then at the very end here, we're going to go ahead and put in the root node. So let's say internal node, root node needs to be, 1 second, placed into internal node. Why are you doing the whole node 1, node 2? Yeah, I definitely need, yeah. Okay. So let's go here. Root node needs to be placed in internal and external nodes. And now what we're going to say is the following. So we want initial nodes, I believe, dot top, because that should be the root node. So let's go down here and let's write that out. Should be returning just the root node in initial nodes. Here we go. Now we're going to say the following. So it should be, where are we here? Internal nodes dot pushback. Oh, I'm sorry, not internal nodes. My bad. I don't know what I was thinking there. It's just internal dot pushback. And I want to push back initial nodes dot top. Good. Okay. Yeah, so I had the 2 nodes because we did need to add them together for parent nodes. Let's go ahead and remove that. Remove that line. To be fair, you shouldn't even be using priority queue here. Gaston, you're the one that told me to use a priority queue. So yeah. Why wouldn't we want to be using priority queue? I think the priority queue is actually exactly what we want here. So now that we have these guys returned, let me go and let's do this. Write and quit. What do I want to do? Using std vectors for the internal and external nodes is fine. Okay. So let me do ls here, and let me see. Let's go into Huffman visualization. 1 second, Huffman. What was I trying to do there? Vi Huffman visualization dot cpp. So let's go down to main, and let's see what we got. So main's here. Jack and Jill went up the hill. Let's see. Where did we do this? I can't speak today at all. Where did we find Huffman? I'm looking for Huffman. There we are. STD, Huffman tree, final tree. Oh, we did 2 pass Huffman. Oh, okay. Let me see what we do in 2 pass Huffman. VI, what do we want here? Let's do Huffman.cpp. And let's look up 2 pass Huffman. Oops, my bad. 2 pass Huffman. Okay, there we are there. It's great. 2 pass Huffman. So we should call Huffman inside of 2 pass Huffman. Yep, here it is right here. So now when I output stuff, what I mean to say is that such a micro optimization don't imply an improvement of some magnitude. That 20% will be achieved with just a slightly better processor as well. So to be fair, yeah, that is kind of true. We could just throw more computing resources at a system and that'll work. It depends on what systems you're working on. For me, I usually try, although I end up usually failing at optimizing the code when I can, simply because, you know, sometimes my code's running for weeks on a cluster, and 20% optimization is like a day, you know, so that's kind of nice. But it depends. So let's see, final tree.root is equal to Huffman. Wait a minute. Wait a minute here. Final tree.root is Huffman. Do we need the root tree? Yes, we do need the root tree. Let me go ahead and make this one more time just to make sure it is working. Oh, sorry. Make error 93. DD DD. Write this, go over here, and let's make it. And let's see how it breaks. I've got a feeling it's not going to work as well as we hoped. Oh, never mind. Okay, it worked exactly as we anticipated. In actual real-world applications, such optimization should be taken into account. You're right. To be fair, there is a lot of slow software out there nowadays. So let's go back down to our 2-pass Huffman. Where are we? In depth, in code, 2-pass Huffman. Here we are. So we have our Huffman tree right here. Now let's go through and let's output the internal and external nodes. Outputting the weights of internal and external nodes. Okay, so here's what we're going to say. Let's use size t. If I can remember how to do a for loop, size t. I equals 0. I less than. That was meant to be a semicolon. Somehow I didn't know. I less than internal dot size. We're gonna do plus plus I. There we are. And tell it to Google or Facebook, where a few percent of improvement literally means millions of dollars. Yeah, let me think. Yeah, I guess it could be millions of dollars. Okay, so now we're gonna do this. Internal of I. Let's go here to I std cout. Internal of I, pointing to weight. Good. In this case, you might want to use range for it. Yeah, we could. End line. Let's go down here and let's do the same thing. Yeah, we could totally do that too. So for size t, I equals 0. Again, it just depends. I've already written the loop. It's only going to be here for like 2 seconds, so I'm not that worried about it. Let's go down here and let's do std cout, internal nodes r. Let's go here, new line, and let's go down here, and we're gonna do I less than. Why not? We'll do it that way. Let's do for auto node. 1 second. Auto node in internal. We just do std cout node pointing to weight. Okay, so we go here and we'll do the same thing down here with external. Auto external node pointing to 1 second. Not pointing to. Going through external. Let's go here. std cout node pointing to weight and line. Thanks, man. Let's go here. Add in a new character there. Now, I'm going to add in a new line here, and I'm going to do this in a weird way, but that's okay. So std cout new line, just to give it an extra space. I guess that's all I need there. And let's go down here. Note that you generally don't want auto node, but it's fine in this case since it's a pointer anyway. Auto ampersand or constant auto is used most of the time. Okay, fair enough. So now we're going to do std cout external nodes. Let's see, r, and we do the following, end line. Oh, that wasn't what I meant to do, end line. Good, let's go ahead and add a semicolon there. So you want me to use auto, let me see, 1 second. Auto ampersand constant auto. Okay, fair enough. Let's go here and make it, and let's see how it works. 1 second. We have external nodes are the following. 24 sounds good to me. 121. So we are adding all the internal nodes. Now, one thing that I do find kind of weird is that we have a 24 here. Are there really 24 spaces? Let me see. How many spaces are there? Let me see. That's going to be hard for me to count. We should have... Plus references don't work for some containers. Yeah, I like maps. Okay. So final tree.bitmap. What do we want? Create bits. Okay, so now we're going to have the bitmap here. I apologize for hitting the microphone. Let me very quickly output one particular value of the bitmap. So let me do skd cout. Number of spaces is, and then we do this, and we want to do final tree dot bitmap of, I believe space here should work. And I guess, yeah, that should work. A new line. Write this over here to make. Okay, that didn't work. Why didn't it work? Final tree.bitmap. How do I call a map? 1 second. For some reason, I'm being stupid here. Let's go here to... let me just put in like a J or something. Make. Okay, clearly, I'm doing something stupid here. Final tree bitmap. Phrase of I. 1 second. What are we doing up here? Wait map. Phrase of I. 1 second. Oh, is this supposed to be because it's this guy? Bet you that's it. Yeah, that was it. Double and single quotes. My bad. Okay, so what do we have here? Final tree wait. Number of spaces is 11. Okay, so... Yeah, I gotcha. Okay. Every once in a while, I just screw that up. I think it's because I do so much Python encoding lately. I just kind of get mixed up between single and double quotes. Okay. So that's very interesting because it means that we have an external node. Yeah, that's actually super interesting. Let me go to internal nodes. We don't have any of these nodes that are of weight 11, which we should have. We should have a weight 11 number of spaces. So... Also, we have two 10s. Let me do this. For the external nodes, let's not output external node weight. Let's output a couple different guys. So we're going to do external node, node pointing to key, and then tab, and node pointing to weight. Make it. Okay, let's see what we got here. So, exclamation point. Space says it's 24. What? Are there 24 spaces? It should be that there's only 11. Number of spaces is 11. Okay. Number of spaces is bitmap. Oh my gosh. One second. Yep. Okay, that would be my problem. 1 second. Let me. Yeah, it's 24. That was me being an idiot. Sorry about that. Okay. I was using, the bit encoding. Yep. Well, that's what I get. Sorry about that, guys. Okay. That explains what the issue was there. Good. This is just a small scale test for me. Man, I'm tired. I'm thirsty. Gosh darn it. Hungry. Today is just a day. Okay. So what do we have here? External nodes are exactly what we want them to be. Internal nodes are exactly what we want them to be. This means that we are appropriately outputting things as I would expect. So let's see, external nodes here. Let's go ahead and remove this line. And let's see what we need to do next. So we have the external and internal nodes coming out of two-pass Huffman. So if we do the two-pass Huffman algorithm, we should probably also output the internal and external vectors. But let me see, I think they're already in the Huffman tree. So let's go here. Let me see, what do we have here? Node reserve, an internal node, internal reserve. I think if I go into vi, Huffman.h, we should have in the Huffman tree, which should be down here. Yeah, we have two vectors for internal and external. So what we need to do instead of creating them here is we just need to remove this line and remove that line. And we want to do final tree dot internal
reserve final tree dot external reserve. We do that. Then we get on here and do final tree internal, final tree external, internal, and final tree external. I'm not sure at all. Let's make it. Let me see. External is not declared in the scope. Fair enough. Let's go to 240. What do we have? Final tree initial nodes. Yep, these have to be final tree dot internal, and of course final tree dot external, and then we'll be good to go from there. 1 second. Final tree dot external. Write this. Go over here. Make it. And now we should have a list of internal external nodes, or vector of internal and external nodes, being output from this particular function. We have the final tree root weight. Everything should be good. So we are set to start working on some stuff for the Vitter algorithm at this point in time. We got to do a couple things first. So now we have the nodes, the internal and external nodes. That works just fine. So now let's go into the Vitter algorithm and let's see what we need to do. Run quit. Okay, let's open up Vitter. So we have this guy that Gustron wrote a few days ago now, almost a week ago, I guess, to find the leader of the block. Let's go ahead and test this guy. So it should, if we are correct, it should find the leader of any particular block given any particular node. So let's go through and let's work on this real quick. So the first thing we need to do is in main, let's go through and do our 2-pass Huffman algorithm to create a final Huffman tree. So this requires some sort of string. Let's go ahead and create a string. Let me think here. So we're going to use the same string as we have been using just to keep everything consistent. So let's go into VI Huffman visualization.cpp. Let me go down real quick to the bottom here. Here, so Jack and Jill, no, I think auto amp constant. Let me see. Okay, so that's the string phrase. Jack and Jill went up the hill to fetch a pail of water. That's what I want. Here's what I'm going to do. I'm going to, I'll copy this over here. Why not? Okay, let's do write and quit. Vi vitter.cpp. Go down to main and let's create the string phrase. Here we are there. And I have to do one thing because I have to do one thing. Sorry about that. Just because when I copy things from a terminal, it doesn't copy the whole line, yada yada. Okay, so string phrase. What do we want to do? We want to, now we want to read this into 2-pass Huffman. So we're going to say Huffman tree is going to be equal to, oh, actually, we should probably just call it tree or something like that. Is going to be equal to 2-pass. We do have Huffman.h being read in, so this should be okay, Huffman. And we want phrase. 1 second, phrase. Good. So let's go ahead and read this in, make sure it works. Now, what do we need to do to make it? Let's go through and let's modify our makefile for this particular algorithm. So again, we have 2 potential objects that we need to make, and let's go through and let's do that. So let's go into makefile. Okay, so now that we're working on the Vitter algorithm, let's go here. Let's see object Huffman visualization.o. That's fine. Let's go ahead and comment these guys out for now. We'll probably use them again in the future, or at least I will, but that's okay. So now we're going to do bins. Let me think. What do we have here? Bins.cpp. That's good. So bins is going to be equal to Vitter. And then we go down to objects. It's going to be equal to Huffman.o and also Vitter.o. At some point, we'll be using Huffman visualization too. We just have a whole bunch of different things here going on. But for now, since we're just doing the Vitter algorithm, let's focus on that first and get everything else working from there. So what do we do? Huffman visualization. Bins is Vitter. So down here. Sorry about that, guys. Well, let's go ahead and do this. So it should be /Vitter, and we should be good. Hey, Full Nerd 33, what's up? Okay. So I think, unless I'm missing something, this should be everything that we need to get this to run. So let's go ahead and write and quit. Let's make it. Missing separator. You mean, oh, of course I do, because every single time it happens, I always put in 8 spaces instead of a tab. Make. Let's see. Okay, so this looks like it's almost working, but not quite. So node find leader, this is what we need to do. Let's go up here and let's fix some things up. So let's do this to be std, and let's see, what else do we need? Finally, it looks like it could be shortened. Could be. We'll get into that in a second. So let's see. Expected a comma. Internal was not declared in this scope. Now it is. Block member was not declared in the scope. Node block member. Okay, so it doesn't like that. Tree was not declared in the scope. Of course not. 1 second. Let me go over here. Let's fix all these problems. Huffman. Tree. Right over here. Now let's make it one more time. Let's go ahead and clear. Let's see what we got here. Make. Okay. So it looks to me block member is not captured. Not captured. Let me see. Return n weight equals block member weight. Block member. What does it mean block member is not captured? I've never run into that error before. Of course, I don't usually use such tricky code. So let's go through and let's see what we got. Compressed between signed and unsigned integer. That should be fine, right? No problem there. Block position. Internal node block member. Okay. So let me see. We have the node being defined. Block member is not captured. Okay. Find if internal. Okay, let me just Google this error because I have no idea what it means. Is not captured. C++. 1 second. Go over here. Is not captured. C++. See what we got. I don't know how often you need to know the start and end of the block's particular weight, but you could have a block struct that stores a position to the start of the block in both the internal and external vectors. We could do that. Let me see. Lambda of lambda. What do we have? You're using f parameter in the lambda aside from inside a sort, but you don't capture it. Try adding f to the capture list. Okay. No, that's fine. That is my bad for, let me see. So we need to put an ampersand where though. So I guess right up there. Let's add that here. And let's see what happens. Go here, make. Okay, this one seemed to make. Everything seems fine. Okay. So let's see what we got here. Return std find if std begin internal std end internal. Okay, let me see. Block member node. Let me see. Okay, so what do we have here? Return std find if. Because I dislike std algorithms. Let me see. Which std begin end? We're using a lot of std algorithms anyway. Block member node. Wait, 1 second. Is there an std algorithm in here that I'm missing? Std end, block member node n. Let me see. Yeah, I have trouble reading a lot of code because I just was not introduced to it before. So a lot of times Gusterun will do a whole bunch of tricky code and I can't read it. So it ends up being that because I can't read it, I end up not being able to use it. But it depends. Finds the first matching node, then does another find using the result of the find of the first non-matching node after. Let me see, what do we have here? Then it returns the one before the non-matching node. So return std. Let's see if we can figure this one out. Return std find if. Where do we have return? Node block position error should never happen. Return internal block position -1. That's where we have our return right here. Add a space in there. Okay. Internal node block position pointing to weight and not equal block member weight turns before the non-matching case. Let's write that out. Let me see if I can figure this out. So what you're saying is that this entire function will look like this. Node star find leader. Yeah, 1 second. Find leader. So now we have to read in constant std vector node star ampersand internal and node star block member. Okay, let's go in here and let me see. So what you're saying is return here. So you're saying return star std find if, let's see, what do we have? Of std find if, I'm just writing this out to see if I can see, understand. Std begin. Let me see. Std begin internal, and then we have std end internal. Let's do internal. Okay, what do we have here? Then we have block member. Let's go down here. Block member node n. Where are we? Block member node. Where are we? Node n. Okay. I screwed this one up pretty bad. Let's go here. That. By the way, I read somewhere that capturing everything in a lambda is bad practice. Let me see. Node n. So now what we do is the following. Okay, so we did this, and now what we're going to do is open this guy up. I guess close it here. And we're going to say return n pointing to weight equals block member pointing to weight. Okay, let's see. Add in a semicolon there. I guess it ends there. And then there's a parentheses at the bottom here. Let me see. Does this make sense? I guess yes. So there's a parentheses there. std and internal should be doing ampersand block member. That's fine. So I'll go up and fix that in a second. It's a point, so you don't need it by reference though. Okay, now we do std and internal. Oh gosh, this is super complicated. All right, let's just write it all out and let's see how we'd indent it in a second. std and internal. Okay, now what's next? Block member node. Of node star and n, and then we return. This is really super complicated. Let me see. Now we do return n pointing to weight. Oh, 1 second. Weight not equals to block member weight pointing to weight. Add in a semicolon. And then we do parentheses -1. I know I butchered that. I'm trying to figure out how to not butcher it. So let me go here. Okay. Let me see if I can figure this one out. Actually, now that I think about it, you could just define the block to start with the leader, which makes the second find if completely redundant. Let me think. Good. Let me see. Where did I do that? And yeah, n pointing to. Appreciate that. Okay, n pointing to weight. So, what are we doing here? We are returning the node. We're find if. Okay, what you said, Gustron, is actually, now that you think about it, you could just define the block to start with the leader, which makes the second find if completely redundant. Okay. Let me think. I guess if the block starts with the leader... Let me see. Open link. Let's see what we got here. Find if. Oh, that looks quite clean. Return find if. SD begin internal, SD end internal. Block member node n. Return n to weight. Block member weight. Now let me think. How would we start each? What is the condition here? Why is this so much simpler to read? That's fine. Why? So what's the difference here? So we have, let's see. So you said if you think about it, you could just define the block to start with the leader, which makes the second find if completely redundant. How do we start the block with the leader? How do we know the leader of the block is, let me think, where it needs to be. Let's do this. Let's go through here. Let's take this guy, because this one's much easier to read. We're going from beginning to end of the internal nodes. I see. So now we do block member node n. Okay, and then what we do is, this is a lambda function where we have block member node n, and yeah, okay, that seems fine to me. Return n pointing to weight equal to block member pointing to weight. Okay, so we are going through the entire list of internal nodes, and we're basically just outputting the node that matches here. Okay, that's fine. Good. Man, I just hit my finger on the desk, and it's kind of hurting. Dang it. Okay, that's good. That's good. Let's go. Yeah, we are doing those insertions. So when you say first, you mean, let me think. Okay, so let's go through and let's just try this real quick and see what happens. So I'm going to comment these guys out and go down here, comment this guy out too. Good. And now what we want to do is put in that new function. So we do return find if. There. So what we need to do is still do the find leader guy. So let's go here and we'll do node star find leader. Okay. And we just copy this guy here. There. And let's go down here to the bottom. Add in someone there. Add in a couple spaces. Here, there, and there. And just to make this a little bit... Not sure how to do this one. Maybe something like that. Not sure. Okay, so you're doing insertions to internal and external. Okay, so let's just go ahead and write this. Let's see if it makes. I expected a semicolon on 32. Let's go to 32. Of course you expected a semicolon. Let's go here. Semicolon, write, make. Okay, this one makes just fine. Now let's see if we can find the leader of the block. So what we want to do is, let me think. When we're inserting the elements into our... one second. When we are inserting the elements into our internal and external vectors, what we want is the highest weight then, because that will be... wait, let me think. Give me a second to think about how this is drawn. It'll be WX. Let WX be all the nodes, certain weight. Yeah, that's what I figured it was something like that. So let's go here and let's see how we would do that. So page, new page before. Here's how we're currently drawing the tree. We're going through and we have all of the external nodes being drawn first. So these are all being drawn somewhere in here. Let's just draw a whole bunch of external nodes. And I'm just going to say this is of weight, I don't know, 2, 1, 1, 1, 1, 2. Okay, that's fine. So we combine these guys together first, then these guys together, then these guys together, these guys together, and finally these guys together. So let's do it. So we have 2, 2, then we have, let's see, 4, 4, and 8 up here. Good. Okay, so the leaf nodes are going to be these nodes right here. So we have a block here. Let's go ahead and just draw out all the blocks. Another block here. Another block here. Let's see, another one here. And finally one here. Okay. So what is the order in which we're putting them into the internal and external nodes? So what we're doing is we're going by order in which they are... how do I put this? They are going in order of... Actually, I think they're already put in the order we want them to be in. Oh, no, they're in the opposite order. Yeah, they're totally in the opposite order. Yeah. Because the leader of this block is going to be... Let's go here. 1, 2, 3, 4. So this guy right here is the leader. I guess I'll do it in orange. That's the leader of that block. This is the leader of that block, leader of that block, leader, leader. Okay, so, dagnabbit. I hit my finger earlier. That's okay. Outsourced web developer. Shout out to Worm. I don't know what Worm is, but hey, sure. Okay. So let's go over here. And again, guys, if you have any questions, let me know. And again, just to be clear and make sure that everyone's familiar, if you're looking for this code, it is available here. So just go to info, down the bottom, click on this GitHub link right there, and it will be, let's see, under the Huffman algorithm right here, or Huffman. Actually, Vitter's not up yet, but I'll have it up by the end of the day. So 1 second, let me grab my water bottle and get a quick sip of water, and then we'll keep going from there. Good. 1 second. Okay. So, let's see. What do we need to do from here? What we need to do is figure out how to put them into the appropriate, or put the internal and external nodes in the vectors appropriately, such that they're in the order that we want them to be in. So how are we going to do that? Well, let's just see if this find leader thing works right as it is now, and then we'll go from there. So quick note, requires specific ordering. 1 second. Note requires specific ordering. And I think we'll put it down like this, kind of what Gustrun said over here. There we are. Good. Okay, so let's go down here and let's see if this works. We have 2pass Huffman, which is returning the internal and external nodes. Now let's see if we can find the leader. So let's go down. Husky, what's up? Yep, you're definitely coding in HTML now. So let's do, here's what I'm gonna do. For, you need the block positions. You'll need something like this. Thanks, Gustrun. You're just writing the code. Let me see. Struct block, internal start, external start, block. Internal start -1, external start -1. Block internal is, internal start. And then we have internal, external start. Okay. Do I get banned if I say roll tide? No, you're perfectly fine. I don't know who you are, because this is the first time I think I've seen that username on this channel. But apparently you knew that I went to Auburn University. So I don't think that's in my information. So you must be someone that I know. So hello. Thanks for coming in. 14 Waj Si Chow. That's absolutely great. Okay. So what do we do from here? Good. Okay, so what we want here is block internal start -1, external start -1. Okay. Let's see. Block internal is external X. It's on your Twitter. Okay. It's on my Twitter. Then you're fine. I thought you were someone I knew from Auburn. But that's okay. So actually I'm in Okinawa now. I think I put my Twitter to stay at Auburn for some reason. I should probably switch it so that I'm in Okinawa. Yeah, probably should. I've been in Okinawa for 2 years now. Okay, so what do we want here? I have family from Alabama. Roll Tide versus War Eagle is crazy with them. Yeah, actually, I can remember. I'm not sure. I'm looking at it right now, Zedison. But actually, I can remember in elementary school when I first moved to Alabama, they actually split the entire class into Auburn versus Alabama, and I didn't know, no idea. I had absolutely no idea what either one was. I didn't know they were football teams, no idea. And so here I was, and I was just standing in the middle because I didn't care for either one of them. And I was like completely ostracized. Like people hated me because I couldn't pick a side between Auburn and Alabama. And I was like, I don't know, okay, Auburn sounds better. So I went to Auburn's side. And when I went for college, it ended up being that I had to choose between Auburn and Alabama again, and I was just like, I guess I'll go with Auburn because they're an engineering school, so that's good. So I don't know, it is crazy, and I hate the fact that they actually looked down on me for not having a team. It was weird. Okay, so let's go. Unordered map. Let's see, block positions. So if new node is leader, block positions node weight, internal start index. Okay. Not like we're using smart pointers here though. Yeah, okay. So let's see. Internal block, struct block. If new node is leader, unordered map in block positions. Oh, I see what you're doing here. Okay, so we have block. Okay. We have int. Okay. So if we want to find block 1, we go in and we put 1 into the unordered map to find that particular block, to get all the block positions, and the block positions are going to be of struct block, which is good. Okay, yeah, that's quite nice. And if we do internal new node is leader, good. Okay, so let's do that because this makes more sense anyway. than whatever I was gonna do. Gosh darn it. Bit byte bosh. Hey, what's up? So where we're gonna do block. Let's go here. And let me add these lines in. So we have internal start, external start. Let me see. Let me go ahead and add 2 spaces to keep notation the same. Let's go here. Dot. SD vector node internal external. I'm gonna leave that in there for now. It should be okay. So now what's next? What we need to do is unordered map of int block positions, and then what do? If new node is leader, block positions node weight internal. Let me see. Internal start equals index. Okay. So let's see. What do we have? We want a map. Do any of you guys write with Java? I'm being forced to learn it for university. Unfortunately, or at least I don't think very many of us on this particular channel do Java. We mainly do C++ here. That said, it's not like there's anything wrong with Java. It's just not used for the problems that we work with. I think it's good for Android development and stuff like that. Yeah, I've only used it a few times. It's not something I would ever claim that I'm proficient in. But, you know, there are other languages that we might be able to help with, particularly C++, or maybe Python or Julia or something. Okay, so let's go down here and let's see what we got. So we have unordered map int and block positions. I like that pretty well. So let's go here and let's add in include unordered map. Okay. Gustorn barely does Java. I don't think it really counts. Okay, so we should have a main function down here. Now, what do I want to do? What I want to do is I want to go through. I want to go through, and I want to work with creating this map that we were working on before, I think. So again, the map right here is going to be an unordered map with an integer and block, so we can read in a 1 and we can get the entire block position. So what does the block position have? It has internal start, external start, block, internal start -1. Yeah, so it basically tells us where in the, what am I going to say here? In the tree we need to go and start with. I used Java for some hobby Android projects, wrote some Japanese learning tools for personal use. Oh, that's pretty cool. The Mad Dave, hey, what's up? Okay. So, unordered map, integer, block positions. I only ever use Java for Android development and Minecraft modding. Huh. I didn't know it was useful for Minecraft modding, but I guess I just haven't played enough Minecraft. I figure it's all Java, right? Okay, so unordered map, integer, and block positions. Good. So now we have if new node is leader, block positions. Good. Of node weight, dot internal start equals index. Okay, so let's see what we got now. Go down here. Let's go ahead and create our unordered map. So we're going to do unordered map of what do we want? We want integer, and we want block. Good. Let me very quickly comment this in. Creating a map to so that we may more easily. Oh, how do I put this? Microsoft is trying to rebuild it from scratch without Java, though. Ah, good for them. What are they going to build it with? I guess my question is, what is wrong with Java here? Create a map. So we may call blocks with integers. Okay, so what do we want? I'm just going to give this is the same name as before, block positions. Good. Okay. So what do we need to do? Let's go through and let's find the leader of every individual block. And then what we're going to do is add the leaders in. So what do we want to do? The problem with Java is game development is GC. The problem with Java for game development is the GC. GC stands for, I'm actually not sure. What does GC stand for? Global Convention? I'm not sure. Sorry about that. Oh, I should have figured garbage collection. Yeah, that makes total and complete sense. Okay. So, unordered map, internal, integer, and block position. So, now here's what we're going to do. We're going to go through every element in the tree, in the internal and external nodes, and find the block leaders. So now we have to find the block leaders. The block leaders. Okay. And this might be the last thing we do today. I'm mostly a C# dev now. I don't know very much about C#. It's not a language I've used at all, actually. I've seen Minecraft server instances spending most of their CPU cycles on GC. It's fine. Again, I just don't know much about C#. So what do we want here? Let's go through in a similar way as to what we did before. Auto node in internal. So this is going to be tree.internal. Tree, one second, .internal. Then we go through, and we're going to have to do the same for external. So let's go here. And actually, let me think here. What do we want to read in? We want to read in the block member. Okay. So, sepals for life. I assume that is an image. And with the Microsoft going through open source, I have high hopes for C# Linux development. That'd be interesting. I don't know. I feel like it's weird, you know? I don't know if I trust Microsoft with a lot of stuff. Like, I just haven't trusted them in forever. I had to use Unity for an internship. Never again. Actually, I hear a lot of people like Unity. We are talking about the game engine, right? Not the desktop manager, right? Anyway, it's fine. But I hear that a lot of people like Unity. So let's do the same thing for auto node in tree dot external. Let's go here. Internal first. Now we're going to go through external. Okay, happy little rat. Microsoft open source is a scary proposition. They're still holding back. Yeah, they definitely are still holding back. One thing I'm very happy for, though, is the Bash shell on Windows. On the one hand, yeah, sure, it might hurt the Linux community a little bit, because there might be a whole bunch of developers that only use Linux because it has the Bash terminal, and that's fine. But in the end, it means that you can do terminal games on Windows now, and that's pretty cool. I don't know. I just don't know what to think yet of it. You know, that's the thing. I just don't know if I trust Microsoft as I just don't use anything that is Microsoft, with exception of Skype. So no, it's good. It's good. Again, I'm happy that they're doing it. I don't know. It's like kind of, I've lived so long without Microsoft tools. It just feels like weird. You know, I'm not. Let me point this out. It's not that I dislike it. I think it's great that they're doing it. However, I don't get it. It's like just boggling my mind every time I think about it. And I still don't really intend to use Microsoft tools, so it's weird. Bash works well on Windows in many forms. Maybe. I think the one that most people use is Cygwin, I think, for the terminal emulator, which is perfectly fine, I think, for most things. But I don't know of any other real good Bash shell for Windows, except for using like PuTTY or something like that to SSH into another machine. Pixel Dice 95. Thanks for the comment. No syntax highlighting. Yep. Okay. I like that command, by the way. Okay. So internal first, external next. So what are we gonna do? Maybe it does. I don't know very much about Cygwin. Again, I have not had the pleasure to work with it. So let's see if we got this right. So we're going to go through each of the nodes, and we have to find the leader of each of the nodes. So let's go and do that. So what I want to do is the following. I want to do find leader, which is going to return a node. So we're going to say leader. Let me do this. Node star leader is going to be equal to find leader. And what do we want? We want the vector of nodes that we're working with. So we want internal. And then we also want the node block member that we're going through. So we should just do node here. And this should be okay. I guess there are quite a few bugs to fix, right? So sorry about that. Again, guys, I'm feeling kind of out of it today. Hopefully after working out this morning, it'll be fine. Okay. So find leader internal and external. What do we want? We are doing find leader, internal block member. Okay, so this should be okay, right? Because the block member would be the node itself. Then we just find the leader. And what I want to do just to check this is I want to do std cout leader pointing to, and what do I want to point to? These are internal nodes, so I guess we point to the weight. And let's see what else happens. Let's write this. Let's go over here to make. And let's see where it breaks. Okay, good. So it broke in a lot of places. That's good. Let's go from there. So first is at 21. Block int is int x. Let's see, open source is beneficial for everyone. They can get the community to fix bugs. Yeah, that's true. However, I don't know. I'm always hit and miss. When it comes to open source development, there's always people trying to do new things. And always overwrites a lot of work that other people were working on, if that makes sense. Like, it always ends up being that people prefer to start new projects than work on old projects, you know? Which is fair enough. I totally understand why. Like, for me, I really want a terminal-based video editor. Like, that would be awesome. You just have mPlayer up on the side that's showing the video as it's going through, and then the terminal itself is just like the nonlinear, what do you call it? The nonlinear editor or whatever it's called. I don't remember what it's called. Okay, so let's go through here. Unordered map was not declared in this scope. Well, that one's easy enough to fix. I think we need std in front of that, so let's go to 75. And let's add in an std. Okay, leader was not declared in this scope. Okay. Was not declared in this scope. Internal was not declared in this scope. That's because that one should be tree.internal. Let me see. Happy little rat. Problem with open source is a lack of quality that comes from a lack of responsibility to maintain anything. I've used FFmpeg. Actually, I've used FFmpeg for a little bit of video editing too. In fact, I used to have a series on my YouTube channel that was Idea Factory, where I just ramble for 20 minutes. All of those guys were edited in FFmpeg. So they were pretty easy to edit because all it was just going through, checking the times at which I need to cut it, and then just writing a script to do all the cutting. And actually, I agree with Gustron here. There is a lot of open source software that is of much higher quality. However, there is, on the other hand, a lot of open source software that is not necessarily of the same quality as their closed source counterpart. For example, why do you use bad closed source then? I honestly think that there are a lot of situations where I would prefer to use an open source project. So I don't know. It's just, in my opinion, I prefer to use open source whenever possible. Of course, I'm using Linux, so you know, my choices are mainly open source. But honestly, I've been using a Mac and Windows device or a Mac device for work, and it just keeps freezing on me. There's all these errors that keeps popping up. My sister has a Windows device. I don't know. Linux is so much cleaner and easier to use for me, and freezes up so much less. It is, in my opinion, less prone to bugs than Windows and Mac, which boggles my mind because you have to pay for Windows and Mac. But that is my experience with it. And because I've been using Linux for so long, it's not a situation where I want to switch. Okay, so now let's see what we have. Error, S was not declared in this scope. That's because that should be in EX. Or in ES. Let's go up here and let's do that. So what do we have here? Where was I? I was here. Let's do this for external start, so it is the same as the internal start. Leader was not declared in this scope. Let's go down to 80. And let's see what we got. So node leader. I guess we'll just add in a semicolon here. And we'll go down here and say leader. Write this. Let's see what happens if we make that. Leader was not declared in this scope. Super confused here because I totally thought, pick best options from what's available. Just remember that if your commercial project depends on some open source package, you can get really screwed with paid packages. Providers are usually responsible for keeping it working. I'm always surprised how sluggish Windows is when compared to Linux. Yeah, I don't know. So happy little rat. That might be true. But the thing is, with open source development, I don't see how you could potentially be screwed because all you do is step up and maintain the package. You know, so if the package is not maintained, just you do the maintenance, you know, instead of other people doing the maintenance. So if you're a big company that relies on open source projects, then you should be responsible for working with the open source project and making it work for your stuff. And yeah, Gustor, of course I agree. I always end up having so many problems when I go back to Windows, and I don't know. I don't know what the deal is. Like, for me, I feel like it's a no-brainer between Linux and Windows, but everyone else, I don't know. It's like what I'm perceiving is not what everyone else is perceiving. Valve's internal Linux port of the software engine was running way faster due to the OpenGL works compared to DirectX. Yeah, actually, guys, what do you guys think about Vulkan, the new graphics API or whatever? I'm kind of hit and miss with it. Like, on the one hand, I kind of want to learn it. On the other hand, I know I don't have time to learn it, you know? So it's not really hit and miss. Zadison, I guess you are the person to ask then. What are your thoughts on Vulkan? Have you guys been using it? What do you guys think about it? I know it's new. Okay, so let's see. Node star leader. Okay. I'd like to enjoy Linux on my Skylake, but apparently it's still buggy, so I'm waiting. What do you mean, the Mad Dave? Sorry if I misunderstood the comment. Okay, so let's go down here. Leader, find leader. So why is this not creating this as a node? What am I doing that's silly here? After we get this working, we'll see what happens there. Node star find leader. Is it because I put the star in the wrong spot? I don't think so. Make? No, okay. So it doesn't like me calling the leader not declared in the scope. This was me trying to declare it. Node leader. 1 second. Oh, is Skylake a... Oh, okay, I see. It must be an architecture. Haven't actually looked into it. Okay, I see. My bad. Okay. Thanks, I appreciate that. Okay. So let me see. What am I doing wrong here? Why am I not able to define this as a node? For auto node, a node tree internal. Oh, maybe that's it. Let's change this to in node. Let's go here, change this to in node. And let's go here to make. Yeah, okay, that was the issue. Let's go here and change this to X node, just so I don't make the same mistake again. X node. Okay, now let's see what we got here. Let's write this. Looks like we are outputting the weights of all the internal nodes, exactly what we wanted. So 2, 2, 3, 4, 4, 5, 7, 8, 8, 8, 9, 10, 12, 14, 16, 16, 19, 20, everything seems fine. And because the internal node includes the root node, which is of weight 121, fairly confident this is working. So let's do the same thing down here with the external nodes, and let's see what we got. Let's go here, remove a couple spaces here. I think it's 8x, good. And let's change this to X node. Again, guys, I apologize. I'm feeling kind of out today, but that's okay. We got a lot done. That's okay. Even though it might not be as much as we wanted to get done, we're still getting there. So that's good. So we have tree.external. We're going through everything. Let's also output this. So let me do std cout. And what do we want here? External node weights. Leader weight is the following, which is kind of obvious. Let me think here. There must be a better way to do this. So let me go up here. Same thing here. My problem is that obviously the weight of all of the internal and external nodes in the same block are going to be the same weight, right? So I need to find a way to distinguish between the leader of the block and all of the other guys. So I know that this is actually returning the leader of each individual block. So we're going to say internal node leader weight is, and then we do end line. Write this, go over here, make it one more time, and let's see what we got. Segmentation fault. Sweet. Okay. Tree.external. Oh, okay. That might be the issue. Let's change this to external. Here. And let's go right, and let's go to make. A friend of mine said that the leader is always the first one in its block. That's your distinction. Okay, so we have all the external nodes being written out, all the internal nodes being written out. That seems fine to me. So there's also defined order between internal and external nodes, so that's fine too. Okay. Okay, so we are getting there, guys. It's 6:55 in the morning. I'm trying to think of what we need to do at this point. So here's what we've done today, guys, just to make sure we are all clear. We've been through, and we went to the Huffman.cpp file. We went through and we edited that file so that we could return back an internal and external vector that basically has all of the nodes in it that we want. Now what we're doing is we're going through and we're testing this find leader function, which we had some talk about how we want to do that. And thanks Gustorn and Zadiston for going through that with me. I appreciate that. Now, I think, guys, I'm kind of stuck at this point here. And I'll kind of think about it during the day to see what we need to do. But I might end the stream a little bit early today at 6:55 instead of, or at 6:56 or something like that, instead of 7. Just because I think this is probably a pretty good stopping point. We're going through, we are supposedly finding the leader of every block, and then we're going from there. So let me go ahead and write and quit, and let me do the following. ls, let me do a get status on this particular system. So we have huffman.cpp, huffman.h, and the make file that have changed. Let me think. Let me think about how we want to do this. We could commit huffman.cpp and huffman.h, but I don't want to touch huffman.cpp and huffman.h. So what I might do, guys, is instead of committing vitter.cpp, as it currently stands, I might take a step back and we might commit vitter.cpp a little bit later. So I might keep this version on my computer until we have a more complete working version of the algorithm to go with. And then we'll go from there. Good. So actually, guys, I'm quite happy with how far we got today. Again, as I mentioned, actually, if you just maintain the blocks map, yeah. So here's let's talk about it. Vitter.cpp. So it should be trivial to find the leader. You're right. But there's a couple things I need to think about, and the first is ordering everything appropriately, which is fine. I have to think about how we're going to put it in such that the leader of the block is in the order that we want it to be in. That's one thing to think about it. Oh no, closed source software? Where's the closed source software? Okay, so now if external node start not equal 1, return internal start, else if external start not equals 1, return external node external start, else return null pointer. Okay, so what are we doing here? If internal start not equal 1, negative 1, sorry about that, return internal start. Yeah, okay. An external start. Oh, yeah, it'll be closed for like 2 days. I apologize. I just want to get everything sufficiently far along that we do not require a modification of huffman.cpp in order to commit to the repository. Again, guys, I apologize. My my motivation wasn't down, but my my general I just wasn't feeling well today. So I apologize if I was kind of slow or something like that throughout the day. That happens every once in a while, but that's okay. I'm very happy with how far we gotten today. I will take a look at what we need to do from here on to get this vitter algorithm working, and I'll be honest, this is pretty much uncharted territory for me, so we might be moving kind of slowly through this. As always, if you have questions as we're going through this for the next few days, totally let me know, and I will take a step back and do my best to answer those questions as they come along. At this point, guys, it's roughly 7 a.m. I'm going to go ahead and end the stream for today, and I'll be back tomorrow at 5 o'clock in the morning, Japanese Standard Time, like every single day. Well, almost every day. And we'll keep working on this. Hopefully getting a little bit further, getting a lot more done, and hopefully we'll be able to draw a neat little picture, kind of like we have right over there, for the vitter algorithm within a week or two. I think. We'll see how far we get. After that, we're going to be going back to some physics algorithms, which should be a lot of fun. Pretty excited for that. Anyway, guys, have a great day, night, afternoon, morning, evening, whatever time it happens to be your time, and I will see you around next time for the next episode of Simuleos, where we continue working on the vitter algorithm. Hopefully, I will be feeling a little bit better than I am right now. And yep, I guess sayonara, or more matane or something like that. Mata ashita, whatever. See you tomorrow. Thanks guys so much for coming in, and have a fantastic time doing whatever it is you guys do. All right, guys. See you around. Bye, guys.